Okay, we have a piecewise defined function for x squared minus 9 over x squared plus 1 on the interval where 3 is less than or equal to x. And we'll come back, Kirby. And x is less than 4. And also x squared minus 9, where x is greater than 2 but less than 3. And we're looking at a equals 3.
Okay.
So basically, we're looking to see, is this limit is this continuous on this interval? So what we do here is we break each one of these up into the limit as x approaches a for f of x equal to L. Okay, and we find what the limit is for each one of these. And if they're the same, then it's continuous at 3. If not, then we have to do something else. So this will be the limit as x approaches a, which we're given a is 3, for x squared minus 9 over x squared plus 1. So basically, we're just substituting that in, right? 3 squared minus 9 over 3 squared plus 1. And we get here 0 over 10, right? And so that's 0.
Why 0? Is it 0 over 10 because 3 squared over 3 squared is 0?
Yeah, because that's 9, right? 9 minus 9.
Oh, okay.
And so this will be the limit as x approaches 3 for, and then we look at the second one, x squared minus 9. And so that'll be 3 squared, right, minus 9. That'll also be 0. So
Okay.
since these two are the same limit, right, then we can say the limit does exist and is continuous at x equal 3. So if they were not the same, then you would have to say that the limit does not exist. So in other words, if you put in the limit as x approaches a for some f of x, and you get, let's say, 3, and you did another one, x approaches a for g of x, let's say, and that was, let's say, negative 3, then you would say that the limit does not exist and is not continuous on that interval, whatever the interval they give you. And so what you would do is you look at the endpoint. Let's say f of x where f of x equal L had an interval from, let's say, 5 less than or equal to x less than or equal to 6, and then the other one was 6 less than or equal to x less than 7. And if a were equal to, let's say, 6, then you could say, okay, it's not continuous at 3, but, or in this case, this would be 6 and this would be 6, but we can say that it is continuous because a and the left side of this the interval here is less than or equal to, you could say, okay, it's not continuous at 6, but it is continuous from the right as x approaches 6 from the right. So you could say, okay, it's not continuous, the limit doesn't exist, but because 6 is less than or equal to 6, and this is 6, you could say that the limit does exist going from the right. Okay, so you could say that. Okay,
Yes, sir.
all right. Any other questions? So let's go back to our document. And here it is. All righty. So I'm gonna fix that. There shouldn't be two of the same like that. I'll go out with I'll update that.
Okay. Can we do 7?
Number 7. Okay, find the limit of each sequence. All right. So for that one, let's see. Did I use the same one? I'm looking to see if I used the same one for that. If I used a different one. Okay, so for that, okay, so let's see, find the limit of each sequence, then define the limit of each sequence. So for this one, get a fresh sheet here. All right. And we're back to here. Okay, so for number 7, you're given the sequence a sub n is 2n over n plus 1. And so we had to find the limit of each sequence, then define the limit. Okay, so where you had summation of n equal 1 to infinity for a sub n. So basically what you want to do first is find the limit. Okay, because in order to find, because from here you have to from once you find the limit, right? Limit as x approaches a for f of x equals to L, then you can put it into your epsilon delta equations. Less than epsilon whenever x minus a is less than delta. Okay, so you have to find the limit first. So you find the limit as x approaches. Now notice they don't give you an interval. So you have to assume that it's approaching infinity, okay, for 2n over n plus 1. So basically, you're looking at the degree, you compare the degree of the numerator over the degree of the denominator. And basically what you're looking for is you're defining the y asymptote, the horizontal asymptote. If you can define the horizontal asymptote, then you can define the limit. So if n is less than n, then it's 0. If the degree of the numerator is less than the degree of the denominator, then the limit is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit is the coefficient of the highest power for the numerator and denominator. If the degree of numerator is greater than the degree of the denominator, then it goes on to infinity or negative infinity in the negative direction. So in this case, what would the limit be?
0.
Well, is that degree of the numerator less than? So if you have the, basically you're looking at y equals to ax to the n over bx to the m. If n is less than m, then the horizontal asymptote is 0. If n equals m, then and so would the limit be 0. So whatever the horizontal asymptote is, that's your limit as well. If n equals n, then it's going to be the coefficients. So, and then if n is greater than m, then there's no horizontal asymptote. So the limit
1.
as x approaches infinity is either going to be positive or negative infinity, depending on which way it's going to go.
Mm.
So which one of the three does this apply to?
Positive infinity.
Well, so you're saying that the degree, when we talk about the degree of the numerator, we're talking about the exponent. So what's the exponent here for n?
1.
1. What's the exponent here?
1.
1. So that would be basically you're looking at 2n over 1n. So since this is 1 and this is 1, therefore, is it less than, equal to, or degree of the numerator, is it less than, equal to, or greater than the degree of the denominator?
They're equal to.
Equal, right? So therefore, our limit is what?
Two.
Yeah, it's 2 over 1, right? It's the coefficients. It's the coefficients, right? 2 over 1 or just 2. So that's our limit. Okay? So we're saying that the limit as x approaches infinity for f of x, for this f of x equal L, f of x is, in this case, our a of n is 2n over n plus 1, and our limit is 2. So that's what we plug in here and here. Okay? So what's going to go in here?
2.
The 2n, the whole thing. This is the same thing as f of x.
Okay.
So it'd be 2n over n plus 1 minus, okay, what's our limit?
2.
2. Okay, and that's equal to, and that's less than epsilon. Okay. So what we have to do here is we have to figure out what so what we're doing here is for all epsilon greater than 0, there exists a n greater than 0 such that n is greater than the uppercase N. Then we can say that a sub n minus L is less than epsilon. So what all does that mean? Okay, here we have our interval, right? And so if a sub n, we have a first number, let's say we have a second number, and then a third number, and then a first number, second number, third. So I'm graphing roughly what a sub n would be. Let's say at 1, this would be 1, right? At 1, this would be 1. At 2, this would be 2 times 2 is 4 over 3. So, and then, so that would be slightly larger than 1. And you would go, you would have this. So what happens here is that as it gets further away, as this gets further away, tends towards n, then these dots are going to start getting closer together. Okay, so you're looking at, that's where your limit's going to be. So you have to establish, you have to find a capital N where you can say, all right, from this point on, from n on, from this uppercase n on, you're going to come up with your limit. So that's what this is here. So this is all explained in lesson 2.5 video. So you want to make sure that you watch that.
You
So,
said 2.5?
2.5, yeah, this is 2.5. Okay, so I put the lesson that the question is related to. So what we want to do here is we want to take this and find, and then we want to basically solve for epsilon. And then when we do that, then that'll give us our lowercase n. And then what we, from there, we can substitute that in back in for, then from there, we can go ahead and write our proof. So we need to take this and simplify that. So this will be, rewrite this 2n over n plus 1 minus 2 is less than epsilon. So you have to combine these, right? So in order to do that, you have to multiply this one by n plus 1 over n plus 1, and then distribute the 2. So that'll be 2n over n plus 1 minus 2 times n plus 1 over n plus 1. And so that's less than epsilon. And so you can combine, so you have to distribute that 2, right? And you get 2n minus 2n minus 1 over n plus 1 is less than epsilon. And then from there, you solve for n. And then, or you're going to, once you solve for n, then you can say, all right, well, n is greater than or equal to whatever this is here, and go backwards on your proof. So you want to
That'd
want
be negative 1 over n plus 1.
What is it?
Negative 1 over n plus 1.
Yeah. Yes, that's right, because these two n's cancel, right? So you get absolute value of negative 1 over n plus 1, right, is less than epsilon. And, or no, this is 2. This is 2, because the 2 distributes.
I was tripping because I wrote that.
Yeah, so it's 2. Okay, because the 2, that'll be 2n minus 2, negative 2n minus 2, the 2n's cancel, and you still have negative 2. Well, because this is an absolute value, right, the negative can go away. And so from there, that'll be 2 over n plus 1 is less than epsilon, and then you solve for n. Okay, and you get n is greater than whatever you're going to get. And then you can go back and rewrite your proof. So take a look at the video on that, on lesson 2.5, okay? And then I'll explain. All right?
Okay.
All righty. So any other questions?